Here we're going to try to find an expression for this integral. It seems rather formidable. We have t to the a minus 1 divided by the natural log of t, and we're going to integrate from t equals 0 to t equals 1. There certainly is no standard formula to apply, so we're going to go ahead and differentiate it as you saw us do in the previous 2 or 3 videos, and see if that process can help us find a way to get an expression for our original integral. The playlist is at the website digital-university.org. If you go there and click on free calculus videos and then scroll down to where it says differentiation of integrals, you see the first 3 videos in that series were devoted to developing the Leibniz formula for differentiation of an integral. This is the most general form here. And again, we took some time to develop this, so hopefully everybody is familiar with it. We're going to apply it to this problem. Fortunately, the limits that we have are both constants. In the most general formulation for the Leibniz rule, we have functions that are limits. That's why we have this term and this term. Well, if we have constants, then that derivative is 0, that derivative is 0, and we only have this term to deal with. And that just, of course, tells us that if we're taking, this is our integral, and we're taking the derivative with respect to x, we simply do the differentiation inside of the integral. And for our problem, we could ignore this term and this term because our integration limits are constants, not functions. And remember, we had explained earlier in our previous videos, if we have, say, the integral of f x of t dt, and we have some limits here, they can either be constants or some function, but this will give us some function x. Originally, when we integrate it, we will get a function of x and t, but then whatever these limits are, we substitute that in there for t, so we have only a function of x. Now, this integral right here is going to be some function of a. If we could integrate this, it'd be some function of t and a, then we'd substitute in 0 and 1 for t, leaving only the variable a. So that integral is some function of a. So let's take the derivative of it with respect to a. So that equals, and then we just simply take the differentiation process inside of the integral. Take the partial, and now we're doing it as a partial derivative because our function here is a function of t and a. So we have to take this partial derivative. Let's take this to the outside. We have the partial with respect to a of t to the a minus 1 divided by the ln of t. Of course, we treat t like it's a constant, so because we're differentiating with respect to a, so this will equal just 1 over the ln of t. The partial of this is going to be 0. Then we have the partial of t to the a. except we didn't write it as a partial sign in here. So we have 1 over the ln of t, treating this as a constant. The partial of this, that's 0. So we have left the partial with respect to a of t to the a. And this, that is just simply t to the a times the ln of t. Remember, if we have, say, x to the c, and we take the derivative of it with respect to c, that equals x to the c times the ln of x. So here we're taking the partial of t to the a with respect to a, so this is just t to the a times the ln of t. And then we see that this and this are going to cancel, so what we have left is this equals t to the a. So the partial of this with respect to a is just t to the a. So let's write that in. And remember, now this step right here, that's just the equivalent of this step right here. We just simply move the differentiation process right inside of the integral. We've been doing that all along. And this is just t to the a. So we have the integral from 0 to 1, t to the a dt. So the derivative of this integral is this, and of course we know what this is. That's t to the a plus 1 divided by a plus 1. T goes from 0 to 1. So we have right now is this derivative equals 1 over a plus 1 times t to the a plus 1, where t goes from 0 to 1. So this equals 1 over a plus 1 times, put t equals 1, 1 raised to any power is just 1. Then we have minus, t is 0, that's just going to be 0. So this equals 1 over a plus 1. So the derivative of our integral with respect to a is just 1 over a plus 1. Let's go back to here. The derivative of our integral, we abbreviate it like this. di dA equals 1 over a plus 1. So let's multiply both sides of the equation by dA. And we have di equals this, so let's integrate. And we have I of a equals, and that'll just be the ln of a plus 1, plus some arbitrary constant of integration. So now we have an expression for I of a. So we started with this integral, we took its derivative, and we found that its derivative equals this. So that gave us an expression, this, that we can integrate. So now we have an equation that actually involves IA, the integral, equals what? The natural log of a plus 1 plus some arbitrary constant of integration. So let's go back up to here. There is I of a, and that equals the natural log of a plus 1 plus an arbitrary constant. So now we have an expression for this integral that before we did not know how to solve. Now what happens if we try to evaluate this expression when a equals 0? So then we'd have t to the 0. Well, any number to the 0 power is just 1. 1 minus 1 is 0. So for a equal 1, this is just going to be 0. So we have 0 equals, not a equal 1, a equals 0, sorry. T to the 0 is 1. 1 minus 1 is 0. Then that will equal here, a is 0, the natural log of 1, plus the arbitrary constant of integration, c. But the natural log of 1, that's 0. So c is 0. So there's the solution to our problem. And if we didn't go through this sort of convoluted process of, here we had an integral, we did not know how to evaluate it. There's no standard methods for it, but we could find a derivative of it. Then we found a derivative of it. That gave us a form that we could work for, that we could integrate, that eventually gave us this expression right here. So again, it's another demonstration of how we can use the derivatives of integrals to sometimes solve an integral that initially seemed like would have no solution.